Hello. Let's now go one step further and try to determine the equation of the tangent to the function f of x, which is given by 5x times 3x squared minus 2x plus 1 at power 7 when x equals to 1. Not only that we're going to apply the chain rule, but we have to understand why we do that and also practice applying the chain rule once again. In order to determine the equation of the tangent to a function f of x, we need to know two things that are very important: the slope and a point on this tangent, because the equation of the tangent to a function is going to be given by a linear in a line, and it's going to be of this form: y equals to mx plus b. M is the slope, as we know, b is the y-intercept. The most important part is to determine the slope. But as we know, the slope of the tangent is nothing else than the first derivative. So, in order to determine this m, the slope, we're going to determine the first derivative. So, if we look at this expression, what we see, because I told you this is the first and the most important step, is to identify what exactly do we have in order to know what rule should be applied. So, I can see 5x as an expression multiplied by this other expression at power 7. So we first gonna approach it as a product. So we're gonna apply the product rule and continue differentiating using the appropriate rules as required. The product rule, it's going to give us the derivative of the first term, so ddx of 5x times the other expression 3x squared minus 2x plus 1 at power 7 remains unchanged, plus 5x now is unchanged times the derivative ddx of 3x squared minus 2x plus 1 at power 7. The derivative of 5x is going to be 5 times 3x squared minus 2x plus 1 at power 7 plus 5x times, now we have the power of a function. Obviously, we have that expression at power 7, so we're going to apply the power of a function rule. This is going to continue to be multiplied by 7, the power, times 3x squared minus 2x plus 1 at power 7 minus 1, so 6, times the derivative ddx of the expression in the parentheses only, 3x squared minus 2x plus 1. And in the next step, I'm going to separate the common factor in front of this expression, because as you can see, I have 5 and then I have this expression 3x squared minus 2x plus 1, and I'm going to take the smallest power as a common factor. What I'm going to end up with is going to be 5 times 3x squared minus 2x plus 1 at power 6 times the first term had power 7, so I'm going to keep again 3x squared minus 2x plus 1, plus in the second term we already factored out 5, so we're not going to have that anymore, so it's going to be only 7 times x times this parenthesis at power 6. It's already factored out completely, so the only thing that's remaining after 7x is the derivative of the expression 3x squared minus 2x plus 1, which is 6x minus 2. We did two things in this step. We found the common factor and isolated it in the front of the expression, and we also derivated that final parenthesis. And now all we can do is simplify the expression in the second parenthesis a little more. This is going to be 5 times 3x squared minus 2x plus 1 at power 6 times, we have 3x squared plus 7 times 6, which is 42, so it's going to be 45x squared, minus 2x minus 14x is going to be minus 16x plus 1. So this is the expression for the f prime of x, for the first derivative of this function. But in order to determine the slope, m, as I mentioned, at that particular point when x equals to 1, we have to determine f prime of 1. Let's calculate that. It's going to be 5 times, everywhere where I see in the expression above x, I'm going to replace that with 1. So 3 times 1 at power 2 minus 2 times 1 plus 1 at power 6 times 45 times 1 at power 2 minus 16 times 1 plus 1. And now here we're going to have 5 times, the first parenthesis is what? 3 times 1 minus 2, which is 1, plus 1, which is 2. 2 at power 6 is 64, times 45 minus 16 plus 1 equals to 30. So all this product is 9600. We can also determine one point on this tangent. We don't necessarily need the y-intercept, but we need a point. And what is the easiest point to calculate when we have a value for x would be to calculate a value corresponding to that x value. And that is going to be f of 1, or the y value when x equals to 1. So let's calculate f of 1. This is going to be 5 times 1 times 3 times 1 at power 2 minus 2 times 1 plus 1 at power 7. So this results into 5 times, in the parentheses there we have 3 minus 2, which is 1, plus 1, which is 2, at power 7, it's 128, and 5 times 128 is 640. And that means that our tangent is going to go through the point 1 and 640. So we have one point on the tangent, and we have the slope of the tangent. That means that we can now determine the equation of the tangent very easily. By definition, the slope m, or as we determined 9600, equals to delta y over delta x. In other words, y minus the y value of one point on that tangent, which we determine to be 640, over x minus the value of x of that same point on the tangent. So 1. Let's reorganize this expression to isolate y on the left. So we're going to have y minus 640 equals to 9600 times x minus 1. And keeping only y on the left side, we're going to have y equals to 9600x minus, performing the operation there, after we move the minus 640 on the right side, changing the sign, that is going to result into minus 8960. And this is the equation of the tangent to f of x when x equals to 1. You've seen that this type of problem is very common in this course of calculus and vectors, so it's best that you understand this concept of determining the equation of a tangent regardless of what rules you may need to apply. It's a good practice either way. I hope you find these examples useful. Thanks for watching.